Hi, in this episode we're going to look at the anode ray tube experiment. Anode rays are similar to that of cathode rays, except that these are uh, these have a different charge on them. So in this episode we will familiarize ourselves with how anode rays are produced and how this discovery helped the investigation of the atomic structure. This is the missing piece in Thomson's model. And this is the first demonstration that all matter has positively charged particles. And then they were named the nucleus later. And isotopes were discovered. Isotopes are the elements that have the same atomic number but have different atomic masses. So these were very first time discovered. And most of the mass was found to be associated with positively charged particles, or these anode rays. Most of the mass of the atom was found on the anode ray particles. And so we will then put these things together into the experiment of the anode ray tube. So anode ray tube is very similar to that of the cathode ray tube. I've shown this a picture here with essentially the same as the cathode ray tube, except the electrodes are interchanged. So it's a gas discharge tube which is filled with a very low pressure gas of any kind that you're interested in: neon, argon, krypton, helium, whatnot, hydrogen, and a strong electric field is applied to produce the radiation. And so, as in the cathode ray tube, I have simply shown a reversal of the charge field. So you have a basic bulb. At the bottom of the bulb, you have the anode instead of the cathode. Anode is negatively charged, and so it could emit anode ray particles, particles emitted by the anode called anode ray particles. At some distance from it is a cathode, and a hole is drilled into the cathode, so the anode ray particles can pass through the cathode and hit the screen. And so you have a screen that is a phosphorescent screen. On the inside is coated with a phosphor material. So when the rays are produced, they can hit the screen and then generate a glow, and so you could track the position of the beam. And that is when there is sufficiently high electric field applied between the anode and the cathode, the atoms, gas atoms are ionized, means they're stripped of their electrons. So now you have electrons and positively charged ions. And so the cathode and anode materials now accelerate the ions so that they attain certain velocity in the electric field as they travel through the electric field created by the anode and the cathode. And the field acceleration makes them move towards this screen. And so they travel in straight lines because their particles accelerated with certain by force due to the electric field. And so they cast shadows just like the cathode ray did. And so these are again investigated by applying electric and magnetic fields. So although these particles were initially generated by Goldstein and these rays were observed by Goldstein, it was Thomson who actually studied them and measured the charge to mass ratio, just as he measured the charge to mass ratio of cathode rays. And so he designed the same experiment. You have a electrical plates put in above and below the beam. So you have a field applied with length L and negatively charged plate on the top, the positively charged plate on the bottom. And so the rays are this time are deflected upwards towards the negatively charged plate through a distance d. And when the gas was neon, he found that actually there are two distinct rays that are produced. So he concluded from this very simple measurement that the neon element neon with the same atomic number must have two different masses associated with it. So it has two different anode rays particles embedded in it. Then he applied a magnetic field and then restored one of them back to its original position and measured its charge to mass ratio, as we discussed in the previous episode. And so the properties of these particles actually depended on the gas used. So this was surprising to Thomson because in the cathode ray experiment, the particle properties did not depend on the gas used. So this was interesting to him. And more interesting is when neon was used, he found two particles having two different masses and about 10% different in their charge to mass ratios. And later these were assigned mass 22 and 20. So he, in fact, discovered isotopes. The mass spectrometer was born at this point. And then Thomson separated these guys based on their E to M values by applying this electric field and then measuring the charges by applying the charge to mass ratio by applying the magnetic field. Matter, therefore, is composed of negative as well as positively charged particles. This was firmly established from these experiments. Most of the atomic mass, of course, is associated with the anode ray particles, and this was concluded not by Thomson's experiment, because E to M charge does not necessarily tell you that. I mean, it indicates, because it's still a ratio, charge to mass ratio. So it indicates M value much larger for these guys compared to cathode ray. But only after the Millikan's measurement of electric charge revealed that the mass now can be estimated, because now we know the charge, therefore we can calculate the mass. Not only that of the electron, but also that of the nuclei could be now precisely measured. So this, now suddenly the entire periodic table came into existence with its atomic weights and atomic numbers and so on. And so the spectrometer, mass spectrometer, was born, and it could be analyzed, all isotopes, all elements, by this approach. In summary, anode rays are used to investigate the structure of the atom further, and specifically the isotopic composition of elements. And the properties of anode rays, of course, depended on the type of gas used, but independent of the anode. Different kinds of rays are produced from the same gas, and therefore it is because of the presence of isotopes. Charge to mass ratio of the gases dependent on the gas chosen. Therefore, the positively charged entity has different mass and charges from element to element. And mass spectrometer was born. Most of the mass was accounted for by the positively charged particles, and this was suspected initially when the measurements were made, but when once the charge of the electron was determined, then it's clear that most of the atomic mass is associated with the anode ray particles. We have a short problem set to provide more active learning. We would like you to describe how two different sets of anode rays are produced from neon. And just an explanation, a few lines, why there are two sets of rays produced from element neon. Explain how atomic weights and atomic numbers of elements are determined by studying the charge to mass ratio of anode rays of different elements. you can send your responses as a PDF to the discussion board.